Mathematical models are used in many disciplines outside of math to study various applications, such as the population and physical examples we've looked at. Now, it is often helpful to leave some constants as parameters that can vary within the application to best understand these ideas. By allowing certain parameters to vary rather than having fixed values, we can study their impact on an application. As some examples, we will build models using these parameters to see how they can help us analyze certain applications. In practice, it is good to run experiments to test if the theoretical results found in analyzing the model accurately describe the results found in the experiment. But it can sometimes be costly or not possible to run these experiments, and then we need to rely on the models. For our first example, consider a tank at T0 that has Q0 pounds of salt dissolved into 100 gallons of water. Assume that water containing a quarter pound of salt per gallon is entering the tank at a rate of R gallons per minute, and the water is leaving the tank at the same rate. We want to find the limiting amount QL of the amount of salt in the tank in the long run, that is, as T increases off to infinity. Notice here that we have two parameters in this problem, Q0 and R. They are both fixed constants in this application, but we're not giving exact values to them. We're leaving them as parameters so we can vary them if we need. To find the limiting amount QL, we want to know something about the function Q of T, which gives the amount of salt in the water. But the information we're given is about how the amount of salt is changing. So we want to set up a differential equation as we did in other mixing problems. We'll look at dq dt, the rate at which the salt is changing, by splitting it up into the rate at which salt is coming in minus the rate at which salt is going out. The rate can be calculated in terms of our parameter R. The rate in is 1/4 times R. 1/4 is the concentration of salt in the water in pounds per gallon, and R is the rate at which the water comes in gallons per minute. So this rate 1/4 R is in pounds per minute. And the rate out is also in terms of R. Here, the concentration is the total amount of salt divided by the total amount of water. The total amount of salt is Q divided by the total amount of water, which is 100 gallons. And the rate at which the water is leaving is the same at which the rate the water is coming in is R. So the rate at which salt is going out is the concentration, Q over 100, times the rate of the water, R. So here we have an initial value problem. The differential equation we just found, which is rate in minus rate out equals dq dt, which we just calculated as dq dt equals R over 4 minus QR over 100, and we have the initial condition that the amount of salt Q at 0 is Q0. This differential equation is a linear one, but it's not in standard form. So by adding QR over 100 to both sides, we'll get it in standard form as dq dt plus Q times R over 100 is equal to R over 4. And this leads to the integrating factor, mu equals e to the integral of our coefficient of Q, which is R over 100 dt. But R over 100 is just a constant, even though we don't know R. So its integral is R over 100 times t, giving us the integrating factor, e to the R over 100t. Now that we have the integrating factor, we can find the general solution, Q of t equals 1 over mu, which we can write as e to the negative R over 100t, times the integral of R over 4 times mu, which is e to the R over 100t dt. Since R over 4 is a constant, we can pull that outside the integral to have R over 4 times e to the negative R over 100t times the integral of e to the R over 100t, which is 1 over R over 100, or 100 over R, times e to the R over 100t plus some constant of integration c. and distributing r e to the negative r over 100t over 4 into the parentheses, we'll have r times e to the negative r over 100t over 4 times 100 over r times e to the r over 100t plus r e to the negative r over 100t over 4 times c. And we can simplify this a bit because we have r over r and e to the negative r over 100t times e to the r over 100t. So that first term is just 25. And in the second term, r over 4 times c is just another constant. So we can rewrite this as 25 plus k times e to the negative rt over 100, where k is just a new constant, c times r over 4. And now that we found this general solution, we can impose our initial condition that q of 0 is q naught. Doing this, we have that q naught equals 25 plus k times e to the 0, which we can solve to find that k equals q naught minus 25. So the solution to the initial value problem is q of t equals 25 plus q naught minus 25 times e to the negative rt over 100. From here, we can find the long-term behavior as t goes off to infinity. That second term is going to go to 0 since we have e to the negative rt over 100. So as a whole, q of t goes to 25, so the limiting amount, ql, is 25. An interesting observation we can make here is that our two parameters, the rate n and the original amount q naught, didn't have an impact on the limiting amount. No matter what that rate is, and no matter what the starting amount is, the solution will have a limiting amount, 25 pounds of salt, in the tank. This type of observation would be difficult to make if we had fixed values for r and q naught. But by leaving them as parameters, we're able to observe that they did not impact the limiting amount of salt in the tank. Now let's look at a slight variation on our problem. Suppose that we have the same setup as before, and we found the limiting amount to be 25. But now let's add a new condition. If the amount of salt starts at twice the limiting amount, q naught equals 2 times ql is 50, I want to find the value of r, the rate at which water should come in and go out, so that it takes 45 minutes for q of t to be within 2% of ql. Remember, the amount of salt in the tank will never quite reach that limiting amount, but we want to be within 2% of it. To start solving this, let's observe that q naught equal to 2 times ql starts above the limiting amount 25. So we are looking for the rate r so that q of 45 is equal to ql plus 2% of ql. In other words, equal to 25.5. This is because the initial amount starts above 25 and will be decreasing down towards it. So it'll reach that 2% threshold at 25.5. As an equation, we're trying to solve 25.5 is equal to q of 45. And using the solution we found on the last page, that's equal to 25 plus 50 minus 25 times e to the negative r times 45 over 100. To solve this for r, we start by subtracting 25 from both sides, then dividing by 50 minus 25, which is 25, on both sides again, to get 0.5 over 25 is equal to e to the negative r times 45 over 100. And then taking the natural log gives the natural log of 0.5 over 25 is equal to negative 45r over 100. And finally, multiplying by 100 over negative 45, we can conclude that r is equal to negative 100 over 45 times the natural log of 0.5 over 25, which comes to roughly 8.69. So we need the rate to be roughly 8.69 gallons per minute in order for the tank to be within 2% of the limiting amount within 45 minutes. I would like to note that this analysis would be difficult to do without our model in terms of the parameter r, as we would need to run multiple experiments testing different values of r until we found the one that reached the value we wanted within 45 minutes.